Good morning, dear students. Today we can discuss about this actinide series. Okay, so far we have seen this lanthanide series and the next series, that is the actinide series. And also you all know this actinide series, the starting element, it is actinium. Okay, actinium, actinium, actinium with atomic number 89. And this actinium, it is followed by other 14 elements. And these elements constitute this actinide series. So this actinium, it is followed by 14 elements, and these elements constitute this actinide series. Okay, so we can go through this elements in this actinide series. See here, this is the actinide series. Okay, this peach color, this is the actinide series starting from thorium. Thorium, this TH, H is small letter. Okay, thorium. Then comes protactinium, then uranium, neodymium. Sorry, not it is neodymium, it is neptunium. Okay, it's neptunium, then plutonium, americium. Americium, it is small m, americium, then curium, then berkelium, then californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. Okay, so the actinide series starting from the first element, it is actinide, and apart from actinide the other 14 elements are there. That is starting element, the series is named with the starting element, that is the actinide. So next comes thorium, TH, H is small letter. Okay, thorium, then protactinium, then uranium, then comes neptunium, then neptunium, it is neptunium, then plutonium, then americium, then curium, berkelium, californium, CF is californium, then einsteinium, ES, then FM fermium, MD mendelevium, NO nobelium, and LR lawrencium. Okay, so these are the actinide series. So see, next to the lanthanides, the series comes, this actinide will be having its position in the periodic table. Okay, so here you can see in the periodic table, this blue elements, these constitutes the S block elements, isn't it? And here this part constitutes the P block, that is this part from boron, aluminum. This area, these elements will be the P block, and this will be the D block. The green color, it will be the D block, starting from scandium, yttrium. So up to this will be the D block. Then comes the F block element. So this F block, in F block elements, we are having lanthanides as well as actinides. Okay, so the first series is the lanthanide series and the second series is the actinide series. So here this, in the case of actinide series, the electrons are filling in the 5f orbitals. Okay, the electrons are being filled up in the 5f orbitals of the anti-penultimate shell, just like the lanthanides, anti-penultimate shell. Okay, the electrons, the 5f electrons are being entering into the anti-penultimate shell, so they are called as the F block elements. And also see, these lanthanides as well as actinides, they are having very close resemblance. There must not be so much differences in their chemical properties. Even though some differences are there, they have got so many resemblances with each other regarding the lanthanides as well as the actinides. Okay, next you can go through the occurrence of these elements, occurrence of actinides. So one of the most common or the most important element in the lanthanide series, that is uranium, isn't it? Uranium, atomic number, it is 92, and it is a naturally occurring element. Uranium, it is naturally occurring, and also you all know it is a radioactive element. Uranium is a radioactive element. Then again, coming to the first element, that is the thorium. Okay, thorium with atomic number 90. Thorium, see, it is almost 10% of this thorium, it is present in monoxide sand. Okay, it is present in monoxide sand, and also in the in monoxide sand, it is present in the form of phosphate, that is along with some of the lanthanides, it is present, that is thorium lanthanum phosphate. In this form, this thorium is present in the monoxide sand. This is thorium lanthanum phosphate. Okay, then the next occurrence of thorium, so this is first one in monoxide sand, we can see thorium. Then in the second one, in the second case, it is obtained from thorite, THORITE. Thorite, that is thorium silicate, THSiO4. Thorite, thorium silicate. Okay, so that is the second occurrence of thorium. Then again, uranium. Coming to uranium, it is extracted or it is isolated from pitch blende. The ore of uranium, it is pitch blende, PITCHBLENDE. Uranium, it is it can be obtained from pitch blende, and the formula, it is uranium oxide. It is in the form of oxide, UO2. Okay. Then some other artificial elements present in the artificial radioactive elements present in this lanthanides, they are actinium, AC, then protactinium, PA, then comes neptunium, NP, and plutonium, Pu. So these are some of the artificial radioactive elements present in the lanthanide series. So this is the general characteristics or some of the general features of actinide elements. Okay, you have to go through this ores, that is thorium from monazite, then thorite, then uranium. We can obtain it from pitch blende. Then some of the artificially occurring isotopes are this actinium, then protactinium, then neptunium, then plutonium. Okay. Then the next heading, that is the transuranic elements. Transuranic elements. See, transuranic elements means elements with atomic number higher than uranium. Elements with atomic number higher than uranium. Atomic number higher than uranium. They are called as the transuranic elements. See here, elements from starting from uranium or higher than uranium, that is neptunium, plutonium, americium, then curium, berkelium, californium, einsteinium, fermium, mendelevium, then nobelium and lawrencium. These are transuranic elements. So these elements we can call it as, that is uranium, it is having atomic number 92, isn't it? Then next neptunium, it is 93. So from neptunium onwards we can call it as transuranic elements. Okay. Then the next one, that is the preparation of these transuranic elements. That is, we have to prepare the elements starting from neptunium. Okay. So then the next is preparation of transuranic elements. Preparation of transuranic elements. So usually this these transuranic elements, they are prepared from, or the starting element will be uranium 238, 92. 238 is the atomic mass, 92 it is the atomic number of uranium. Okay, so usually it is the starting compound is uranium 238, 92. When uranium, it is bombarded with a neutron, it's a charge and mass. Regarding the mass, it is N10, isn't it? So neutron, when it is uranium 230, 92, when it is bombarded with neutron, see what happens. This, it will be converted to, see, we can add the mass numbers as well as you have to add the atomic numbers. Okay, so here 238 plus 1, so the formed compound will be 239. Then the atomic number, there will be no change, 92 plus 0, so it is 92, plus gamma rays will be emitted here. Okay, so this uranium 238, it is converted to uranium 239, another isotope of uranium. Okay, atomic number will be the same, mass number is different, so it is an isotope of uranium. Then in the next step, this uranium 239, 92, uranium 239, 92, when this emits a beta particle. Okay, this uranium 239, 92, it emits a beta particle. Beta particle, we can denote it as E0 minus 1. So this is a beta particle. So then we will be getting a compound, a radioactive compound here. And the compound, see, what about the atomic number? 92. Here it is minus 1, isn't it? So here it will be the atomic number, the formed compound will be having an atomic number of 93, isn't it? 93 minus 1, it will be 92. Okay. Then what about the mass number of the formed compound? It will remain the same, isn't it? 239, here it is 0. So the formed compound will be having a mass number of 239. And the compound with atomic number 93, what is the compound? Atomic number 93, it is neptunium. Okay, so the formed compound will be neptunium 93 239. So you have to see whether it is written correctly. See here 239 plus 0, 239. This is 93 minus 1, 92. Okay. So you have to write the equations like this. Okay. So here when uranium 230 92, it is bombarded with a neutron, we will be having an isotope of uranium. Then again it will be emitting a beta particle. Beta particle means E0 minus 1. And again with another product it will be neptunium 239 93. So we will be having neptunium, the first transuranic element, isn't it? So this reaction, it will be going on continuously, so that we will be having the other transuranic elements. Okay. So the next, in the next stage, what happens is that this neptunium will be emitting a beta particle. Okay. Neptunium will be emitting a beta particle. Beta particle means E0 minus 1. Okay. So we can write the equation, and also the atomic number of neptunium, it is 93. Okay. So then neptunium 93, the mass number is 239. Then it will be emitting a beta particle, that is E0 minus 1 plus another element. Okay. So you have to write the equation. So the another element will be, mass number will be 239, no change in mass number. Here it is minus 1. So what about the atomic number? Atomic number will be 94, isn't it? 94 minus 1, 93. So the element with atomic number 94, it is plutonium. Okay. See here it is plutonium. The element with atomic number 94 is plutonium. Okay. Thus we had got this plutonium, isn't it? Then the next one, we have to prepare the next elements, that is americium. Then comes americium and curium. Okay. See here the next two elements are, after plutonium it will be americium and curium. And this americium and curium, it was discovered by the bombardment of uranium 238 92 with alpha particles. Okay. Uranium 230 92, it is bombarded with alpha particles. Alpha particle means helium nucleus, isn't it? Helium 24. Alpha particle, when it is bombarded, one of the product will be, it will be a neutron. Okay, N10. So you can write the equation. So here 230 plus 4, 242, isn't it? 242. Here overall it is 242. Here 1, isn't it? So the formed element will be having the mass number, it will be 241, isn't it? 238 plus 4, 242. Here it is 241 plus 1, 242. Then what about the atomic number? Atomic number, here, see here it is 92 plus 2, 94. Here it is no change. So the atomic number will be 94. Okay. So this 94 element, it will be plutonium. So plutonium 241, 92. And again this plutonium, we will be having plutonium 241 94, and also one more isotope will be obtained along with that. Plutonium 239 94 will also be obtained during this bombardment. Okay. And also see, from this plutonium we will be having this americium as well as curium. So when plutonium 94 241, it emits a beta particle. Beta particle means E0 minus 1. Okay. So what about the resulting element? Atomic number will be the same. Sorry, mass number will be the same, 241, isn't it? Then what about atomic number? Here it is 94. Here it is 95, isn't it? 95. So what about the element with atomic number 95? Element with atomic number 95 is americium, AM. Okay. Americium. So thus we got americium. Then you have to have this curium, isn't it? So curium, it is obtained from the next isotope of plutonium, that is plutonium 239. Then plutonium 239 94, when it is bombarded with an alpha particle. Alpha particle means helium nucleus. Helium nucleus, we will be having proton, sorry, not a proton, neutron. A neutron will be there. Then again 239 plus 4, isn't it? 239, it will be 243, isn't it? 243. Here it is 1. So the resulting one will the element will be having mass number 242, isn't it? 242 plus 1, 243. 39 plus 4, 242. Then what about the atomic number? 94 plus 2, 96. So the atomic number will be 96, and the element with atomic number 96, that is curium, isn't it? So we will be having curium. Cm24296 plus a neutron. So you had got americium as well as curium. Then the next element in the series, that is berkelium, isn't it? After curium it is berkelium. So you have to prepare berkelium, and for berkelium the starting element it is americium. Okay. So again americium 24195. Then it is bombarded with an alpha particle He24. Bombarded with an alpha particle. 2 neutrons will be emitted. 2 neutrons plus here 241 plus 4, 245. Here 2 neutrons are there. So the resulting element will be having a mass number 243, isn't it? 243 plus 2 neutrons. So 245. Then what about the atomic number? 95 plus 2, 97. So the atomic number will be 97. And so the element with atomic number 97, that is berkelium. Okay, berkelium, Bk. Berkelium, Bk. Then the next element, that is the californium, isn't it? So you have to prepare californium. So for californium, curium is bombarded with an alpha particle for the preparation of californium. Curium, that is Cm24296, it is bombarded with an alpha particle He42. Okay, it is bombarded with an alpha particle, and the resulting will be having 2 neutrons. Okay, 242 plus 4, 246. Here it is 2 neutrons, so the resulting compound will be having atomic number, mass number 244. So the 244 plus 2, 246. Here 246. Then what about the atomic number? 2 neutrons are there. Here it is 0, 96 plus 2, 98. And the element with atomic number 98. 98 is californium. Okay, atomic number 98 is californium. Californium, the symbol it is Cf. Okay. Then the next element, that is einsteinium, isn't it? After californium, then comes einsteinium. So einsteinium, it is prepared by, or it is obtained by this bombardment of californium with neutrons. So here we had got californium 25098. So californium 25098, it is bombarded with a neutron N10. Then the first resulting compound, it will be californium C250 plus 1, 251 plus here 98 plus 0, 98. That means the same element californium, but an isotope of californium will be obtained with that mass number 251 plus a gamma particle. Okay. Then again in the next step, this californium 25198, it is bombarded with another neutron. Then again we will be having californium 252. Okay, 25298 plus again gamma particle. Then again this process is continued. Californium 25298, it is bombarded with another neutron to form californium 25398 plus gamma particle. Okay, so 3 neutrons by the bombardment, by using bombardment of 3 neutrons, we get 3 isotopes of californium. And in the last step, this californium 253 isotope, it is ready for the preparation of einsteinium. Okay, californium 25398, it emits a beta particle. Okay, it emits a beta particle. Beta particle means E0 minus 1. Okay, so here it is 253. The mass number will be 253. And what about the atomic number? It is 98. So here it will be 99. And the element with atomic number 99, that is einsteinium, isn't it? 99 is einsteinium. So here we will be having einsteinium Es. Okay, einsteinium 25399. So here comes the, so here in this for the preparation of einsteinium, 4 steps are there. Californium, it is bombarded with 3 neutrons, and in the last step it will be emitting a beta particle, so that einsteinium will be obtained. Okay, so then the next transuranic element to be prepared, that is the fermium. Okay, see here it is fermium. So for that, Einsteinium is taken. Einsteinium, it is bombarded with neutron. Einsteinium is 99, atomic number 99, and the mass number it is 253. It is bombarded with a neutron to form Einsteinium. See, 253 plus 1. Here a gamma particle is emitted. So here 253 plus 1, 254. Then the atomic number it is 99. So you will be having an isotope of Einsteinium. Then again, this Einsteinium 254, it will be emitting a beta particle. Okay, so plus a beta particle E0 minus 1. So the resulting compound will be having a mass number 254, the same. 99, here it is minus 1. So here the mass number it will be 100. So the atomic number. So the element with atomic number 100, that is fermium. Okay, fermium 100. So here we will be having fermium Fm 100 254. Then the next element, that is the mendelevium. Okay, so then remaining three elements, three transuranic elements are there: mendelevium, nobelium and lawrencium. Okay, so the 101 element, that is mendelevium. So this mendelevium can be obtained from this Einsteinium. Okay, so Einsteinium 99 253, it will be bombarded with an alpha particle, helium 42. Okay, it is bombarded with an alpha particle to form N10. See, mendelevium atomic number it is 101 and the mass number it is 256. See whether it is balanced. 253 plus 4, 257. 256 plus 1, 257. 99 plus 2, 101. See here it is 101. So we had got mendelevium. Okay, mendelevium. Then comes nobelium, the 102 element with atomic number 102. So for nobelium, this curium 246 96, curium, it is bombarded with carbon 12. To form nobelium, NO 254 102 plus 4 neutrons. Okay, 4 neutrons. See here 246 plus 12 will be equal to 254 plus 4. 96 plus 6 is equal to 102. Okay, so thus we will be having nobelium. This is nobelium. And then the next element, that is californium, CF 250 98 plus boron 11.5. It is bombarded with boron, isotope of boron. So we will be having lawrencium, LW 257 103 plus 4 neutrons. Okay, plus 4 neutrons. So this is lawrencium, LAWRENCIUM, lawrencium. So we got all the transuranic elements using started from the starting compound uranium, isn't it? So these are some of the methods of preparation of these transuranic elements. Then the next one, we can go through the properties of these compounds. Okay, these elements, these actinides. So first comes the electronic configuration. Electronic configuration of these transuranic elements. So the starting element, it is actinium, isn't it? So actinium, see here the electron filling, it is in the in which orbital? It is in the 5f orbital, isn't it? The electrons will be going into the 5f orbital. So see here, while comparing this 5f and the next nearby 6d orbitals, the energy difference, it is very less, isn't it? Energy difference between 5f and 6d, the energy difference is very less. So what happens is that the electrons can enter into any of these 5f or 6d orbitals. So in some cases, the electronic configuration will be changing. For example, the energy difference is very much less in the case of thorium then protactinium, then uranium. Okay, for these three elements, the electronic configuration cannot be predicted accurately, isn't it? That means the energy difference is very less for these three elements, energy difference of 5f and 6d, so that the electrons can enter either into 5f or it can enter into the 6d. So there is a confusion regarding the electronic configuration of these three elements. And usually the electrons will be entering into the 5f orbitals for all other elements. Okay. Then the next is regarding the oxidation state. Oxidation state. So just like lanthanides, here also the oxidation state of the elements, that is +3. That is very common oxidation state is +3. And for some elements the oxidation state is +2. +2 oxidation states are also there, but it is very rare. Okay. Then for nobelium, it has got a +2 oxidation state. This is NO is nobelium. It has got +2 oxidation state. The electronic configuration, it is F14, isn't it? F14 electronic configuration. So it has got a common +2 oxidation state. Then for americium also, it has got a +2 oxidation state. The electron filling, that is F7 electrons will be there in the F subshell or the F orbital. Okay. And again this +3 oxidation state, see here it is the common oxidation state for lanthanides, and also this +3 becomes more stable with increase in the atomic number. More stable with increase in atomic number. That means as atomic number increases, that is from left to right, what happens? The +3 state becomes more stable. Then some of the elements having +3 oxidation state, that is americium, then curium, berkelium Bk, then californium, then einsteinium, then fermium, then mendelevium, then lawrencium. Okay, so for all these elements the +3 state is the most stable oxidation state. Okay, so for these elements, that is americium, curium, berkelium, californium, einsteinium, fermium, mendelevium and lawrencium, this +3 state is more stable. Okay, then some other oxidation states are for thorium, +4 is stable. Then for neptunium as well as protactinium, for neptunium as well as protactinium +5 is stable. Then for uranium +6 is stable. Okay, these are some of the stable oxidation states. Okay, thorium +4, neptunium and protactinium +5, then uranium +6. Then for plutonium, it can have oxidation states ranging from +3 to +7. Okay, for plutonium +3 to +7. And though it can have these much oxidation states, the most stable one, it is the +4 oxidation state. So +4 is most stable for plutonium. Okay, +4 is the most stable oxidation state for plutonium. Then for americium, the oxidation state can range from +2 to +6. Okay, for americium +2 to +6. Then for thorium to berkelium, from thorium up to berkelium, the common oxidation state is +4. Okay, thorium to berkelium, the common oxidation state is +4. Then from protactinium to americium, the common oxidation state is +5. Okay, so these are the regular trend in the oxidation states. Okay, so thorium, it is +5, neptunium and protactinium +5, uranium +6. For plutonium, it can have compounds with oxidation states +3 to +7. +4 is the most stable. Americium, it can ranges from +2 to +6. Then for thorium to berkelium, +4 oxidation state. From protactinium to americium, it can have +5 oxidation state. Okay, then the next one, we can go through some of the properties of these elements, elements in the actinide series. So first property is that they are all silvery metals. They are all silvery metals, and also they have got high melting point. And also for thorium, the melting point is about 1750 degree Celsius. For protactinium, the melting point is 1552 degree Celsius. Okay. Usually these actinides have got a melting point lower than that of the transition elements. Melting point lower than the transition elements. Okay. These are all points regarding the general properties or the general physical properties. Silvery metals, high melting point, but the melting point are lower than the transition elements. And the second point, so this is the first point. Then the second point, the ionic radii. Regarding the ionic radii increases along the series. Okay. Ionic radii decreases along the series. Ionic radii decreases along the series, and also see here, just like the lanthanides, in the case of lanthanides also there is a regular decrease in ionic radii, isn't it, along that series, and this regular decrease we call it as lanthanide contraction, isn't it, in the case of lanthanides. Here also this actinide series also, they have got a regular decrease in the ionic radii, a regular decrease. Okay, so here also we can call it as actinide contraction, just an analogous term for lanthanide contraction. Okay, here it has got actinide contraction since a regular decrease in the ionic radii, and also the reason it is the same as in the case of this lanthanide contraction. Here also this ionic radii decreases due to the poor screening. This actinide contraction, it is due to the poor screening by the 5f electrons. Okay, poor screening by the 5f electrons. Where in the case of lanthanide contraction, it is due to the poor screening by the 4f electrons, isn't it? So here this is analogous, this actinide contraction is analogous with the lanthanide contraction. So that is the second point. Okay, so then the next property we can see in our next session. Thank you.